Hi everyone, my name is Jiang, and I am honored to talk about our recent work, Fast Parallel Bayesian Network Structured Learning. The work is part of my PhD I did at the University of Western Australia under the supervision of Professors Ajmal, Mian, and Zeyi. This is the outline of my presentation. First, I will talk about the background of our research, then introduce our proposed techniques, followed by some experimental results, and finally, I will draw a conclusion. Bayesian networks are probabilistic graphical models. A Bayesian network is defined by a network structure and a joint probability distribution. The network structure is a DAG G. The node in G represents random variables and the edges are independence relationships between them. For example, there are edges from difficulty to grade and from intelligence to grade, which means the difficulty of the class and the intelligence of a student can influence the student's grade. Meanwhile, each node has a CPD. For example, grade has three possible values A, B, and C, and it has two parents, difficulty and intelligence. Both of them have two possible values, 0 and 1. So the CPD of grade provides the probabilities of grade A, B, and C, given its four different parent configurations. Other nodes also have CPDs, and the joint probability distribution can be factorized into these small CPDs. So the graphical nature of Bayesian networks make them suitable for representing knowledge with uncertainty, and BNs have been applied in a wide range of applications. One crucial task of training BN is structured learning. It is to find the DAG G that are well matched the observed data. One common approach is constraint-based approaches. They test the independencies among the variables and build the structure based on these independencies as constraints. The test is called conditional independence test, such as I given D. It is an independence hypothesis that I and G are independent given D. The CI test is to test whether the hypothesis holds or not. The basic theory is that if we cannot find any set S such that the independence hypothesis holds, then there is an edge between I and G. In this example, since we found the independence hypothesis of I and G, given any possible variable configurations are rejected, we can know there is an edge between I and G according to the theory. Almost all the constraint-based algorithms are based on the PC-stable algorithm. It is named after its authors, Peter and Clark. PC-stable generally contains two steps. Step 1 is to learn the skeleton, which means the underlying undirected graph of the network. Then step 2 is to set directions for the edges. The first step takes most of the total time, so we only focus on step 1 here. It starts from a complete undirected graph and removes some edges according to the CI test. So PC-stable performs the CI test at different depths. The depth means the number of nodes in the conditioning set. It starts from 0 to large to reduce the computation. For example, at depth 0, for each edge in the complete undirected graph, we do a CI test, and we found two of them accept the independence hypothesis. So the two edges are removed after depth 0. After that, we do the same process for depth 1, depth 2, and the difference is the number of nodes in the conditioning sets. The process is repeated until no edges are removed. The key barrier of PC-stable is the long execution time for performing a large number of CI tests. There are many PC-stable implementations in the mainstream BN libraries, but these implementations are sequential and their efficiency can be improved. There are also some parallel implementations on multi-core CPUs. They face some efficiency issues which we will discuss next. One parallel scheme is to use edge-level parallelism. It is coarse-grained and it parallelizes the processing of different edges inside each depth. It simply dedicates all the edges of depth D to all the threads equally. Edge-level parallelism is load unbalanced because workloads for different edges are highly different. First, different nodes have different number of adjacent nodes, so the number of conditioning sets to be tested for different edges can be different. Second, if we find a set S such that the independence hypothesis holds, then the remaining CI tests for the edge can be stopped, which means we cannot know in advance the number of CI tests to be tested. Another scheme is sample-level parallelism. It is fine-grained and it parallelizes among samples inside each CI test. For each CI test, the most important step is to generate the contingency table. The table is generated by traversing the whole dataset. For example, for the CI test I, given D, it traverses the dataset and gets the values of I, G, and D of each sample. Then compute the corresponding cell in the table and add 1 to this cell. So this scheme is to parallelize the traversing of the whole dataset. There are two major limitations of sample-level parallelism. Firstly, it may result in a race condition when updating the cells in the contingency table because each sample contributes to the generation of the table. So we need many expensive atomic operations to guarantee the correctness of the execution. Secondly, the workload of each operation is relatively small and thus cannot amortize the overhead of parallel computing. To address these issues, in this work, we propose a parallel solution called FastBNS. I will present the technical details in this part. At the beginning, I will provide an overview of FastBNS. Firstly, FastBNS employs a CI-level parallelism, which has a parallelism granularity between edge level and sample level. It is implemented using a dynamic work pool. For example, for depth 2, suppose there are 5 edges and 2 threads. Edge-level parallelism tries to equally distribute the edges to the threads. And sample-level parallelism parallelizes inside each CI test. While CI level is in the middle, it tries to parallelize CI tests for different edges. Secondly, we propose 3 techniques to further improving the efficiency of FastBNS. Next, I will describe the details. First is about the CI level parallelism. Our key idea is to use a dynamic work pool, which contains the edges required to be processed and their processing progresses. Therefore, each time we can fetch multiple edges from the work pool, find the next group of CI tests of the edges through their processing progresses, and execute them in parallel. We will use an example to better understand the working progress of the CI level parallelism. For example, suppose we have 8 edges and 2 threads. At the beginning, all the 8 edges are pushed into the work pool with 0 processing progresses. Then, 2 edges are popped from the work pool and assigned to the thread. Each thread is responsible for processing a group of CI tests of the assigned edge. We use group size GS to define this number, which means each thread handles the next GSCI test of the assigned edge or handles less than GSCI test if there are less than GSCI tests remained for that edge. When the group of CI tests are finished, FastBNS makes the decisions of whether the edge should be pushed back to the work pool. Simply put, if the edge should be removed or if the edge has finished all its CI tests, the edge does not push back to the work pool with its processing progresses. So suppose that E7 should be pushed, and it pushed back with its processing progresses GS. After that, 2 edges are popped from the work pool again, and the process is repeated until the work pool is empty. Intuitively, we can think of this process as multiple threads processing multiple CI tests on different edges in parallel, but a thread is never bounded to a fixed edge. We use the previous example to compare three-level parallelism. For each level parallelism, thread 0 actually performs 9 CI tests, while thread 1 only performs 1 CI test. The efficiency can be decreased due to this issue of workload unbalancing. And for sample-level parallelism, it parallelizes inside each CI test, which leads to expensive atomic operations and high parallel overhead. For CI-level parallelism, a thread is never bounded to a fixed edge. When the processing of an edge is finished, the thread turns to process the CI test of other edges immediately, without waiting for other edges to be finished, and thus, it can better schedule the workload among threads. Meanwhile, since each thread holds a complete CI test, the race condition does not occur, and thus it avoids expensive atomic operations and also has a reasonable amount of workload to amortize the parallel overhead. Next, we propose 3 optimizations to further improve FastBNS. First, we group CI tests of the edges with the same endpoints. In the original algorithm, the edges with the same endpoints, such as HDL and HLD, are processed separately. It is inefficient, because in this case we find DL are independent given G when testing HDL. Then the test for HLD is no need to perform. So we will use such 2 edges as one edge to reduce the unnecessary CI tests. And our work pool also contains the processing progress with regards to the state of each step it's currently in. The second optimization is to use a cache-friendly data storage for storing the dataset to reduce cache misses. And the third optimization is performed when generating conditioning sets for the CI tests. We design a combination function which can generate the conditioning set given any depth D and the processing progress that can be obtained from the work pool. Therefore, we don't need to generate all the CI tests of an edge and can save memory to store the indexes of the conditioning set. Next, I will report some key experimental results. We compared our FastBNS with 3 sequential baselines and 2 parallel baselines, and the datasets used in our experiments are obtained from 8 reference Bayesian networks of different sizes. These networks have been widely used for comparative purposes in the literature. For overall comparison, we obtained 5,000 samples from each of the networks. We compared the sequential version of FastBNS with the sequential baselines and parallel versions with parallel baselines. Our sequential version is much faster than Tetrid and the PCLG, and can be up to 8 times faster than the sequential version of BNLearn. And our parallel version is much faster than parallel PC and can run up to 25 times faster than the parallel version of BNLearn. To further investigate the reason, we use Perf Linux profiler to obtain the detailed measurement. The parallel version of FastBNS increases CPU utilization and flows, and compared with BNLearn, both the sequential and parallel versions of FastBNS have fewer accesses to the L1 cache and last level cache, and significantly decreases the rate of cache misses. We compared our proposed CI level parallelism with edge level parallelism and sample level parallelism. We can see that CI level parallelism, the blue line, always leads to the shortest execution time under different number of threads. To better understand FastBNS, we performed sensitivity studies. First, we can observe a smooth improvement in speed ups for all the sample sizes. A large sample size often gets a slightly higher speed up, because each CI test has a larger amount of workload, which can better amortize the parallel overhead. Second, fast BNS can achieve high speed-ups for large-scale networks. For small-scale networks, the speed-up are relatively smaller because they already require short execution time for structured learning, and the parallelization overhead accounts for a large proportion. We also examined the effect of group size on the number of CI tests and execution time. Group size is used in the CI level parallelism. It is a trade-off between the number of CI tests and memory accesses. When group size becomes larger, more redundant CI tests are introduced, while more memory accesses can be reused. We carefully examined the effect of GS. The bars is the execution time and the lines are the proportion of the CI test increase compared to the case of GS equals 1. We observed that the CI test is not too high for some small group size, so 6 or 8 may be a good choice of group size in practice. In conclusion, firstly, we proposed fast BNS for efficient BN structured learning, which exploits the CI level parallelism and employs a series of novel techniques. Secondly, fast BNS tackles the challenges of addressing load unbalancing issues, reducing atomic operations, and amortizing parallel overhead. Thirdly, experimental results show that the fast BNS-seq is up to 8 times faster, and the fast BNS-par is up to 24.5 times faster. Moreover, it has good scalability to the network size and sample size. That's all. Thank you for listening.